So this is the third lecture in the Svādhyāya 1.2, and we will be discussing quotient topology. We'll see some identification spaces. For example, we recall that in the very first lecture we saw that if you take a disk and the boundary of the disk, which is circle, and if you identify the whole boundary to one point, you'll be getting a sphere. Okay. So what we are doing in that example is we are taking a set X and a subset of that set, and that subset we are identifying to one point. Okay. And that sometimes we call as an identification space. Okay. But that's also a quotient space. So because there also what we are doing, we are defining the relation that all the points on the boundary or on the subset is related to y or the point. Okay. So let's see. So let's see the proof of at least the thing that if I have a disk and if I take the boundary, the whole boundary to one point, I'll be getting a sphere. So this is my disk, and how is it defined? So this is set of all x0 or x1, x2, xn such that x1 square plus xn square is less than equals to 1. Okay. And so we saw that d2 is giving me s2. So this should give me the n sphere. And how is it defined? So this is defined as x0, x1 dot xn such that xi square is equals to 1. Okay. So we need to give a homeomorphism from dn mod Sn minus 1. So what do I mean by that? So this means that x is related to x, okay, and or x is related to y if x is on the Sn minus 1, okay. And y, let's fix to the y is some point on the disk. Let's say y is, let's say, some point. So y, I'm fixing some point, okay. So not the set, some point. Okay, right. So this is the thing. So this is now a quotient space, and we want to see that whether this quotient space is same as Sn or not. So we recall that we have a very important theorem which says that if x to y, if we have a continuous map where y is host of x is compact such that the map f preserves the equivalence relation, then I'll be getting a continuous map from this to this. And since y is host of, this is compact, and if this map is surjective, bijective, we'll be getting a homeomorphism. Okay. So let's see what exactly is happening. Let's try to see from D2 to S2 what exactly is happening. So see, so D2, if I'll had a bunch of circles, and if you'll see the sphere, it's like point, then you have like then again it's like this. So this is how you are making a sphere. Okay. What I'll do, so this circle, the outermost circle is going to this point. Okay. This is going to the next one. This is going to this one. And the center is going to the south pole. Okay. So this is how, because see, if you recall the first lecture, we have the picture that if I take a disk and like just fold it the boundary and try to put it on one point, then what we'll be getting is like a sphere. Okay, and exactly this is what is going on. The whole boundary is going to the north pole, and other circles is getting wrapped. Okay, and that will be the these circles on spheres. Okay. Okay. So this is exactly the map we have to give. So what I'll define a map from F from Dn to Sn, and so let's say this is my unit disk. So unit disk, and this is in Rn plus 1, and this is in Rn. Okay. So see, any point here on the disk, how can I write it? I can write it as, I'll take a point X, okay, and what I'll do, I'll take a point X, and on the boundary, so it's let's see, like on the disk. Okay, so I'll take a point here, let's say XY, and just come to the interior. So how will I come? So I'll just take T times XY. Okay, where T is in from 0 to 1. So this T determines the radius. Okay, because what is the radius of this? What is what is this? If I'll do t square x square plus t square y square, so this is precisely t square, because x square plus y square equals to 1. So this is precisely t square. So this will lie on the circle of radius t. Okay, so if I'll write this as, so if I'll write just t x1 t x2 t xn. Okay, so I need to send this to this. Okay, this to the respective circles on the sphere. Okay. Okay. So you see that on a sphere, one determines the height. Okay, and the other determine the radius of the circle. Okay, so that is what we have. That's why we are getting one more coordinate. Okay, so that's why this has n plus 1 coordinate. So I'll just send, so this map you can check. So how will I define this map? I'll keep the same thing that I just told, that I'll take a circle of radius t and I'll sending to sphere of some radius. Okay, so precisely how do I define a map? So this is cosine pi into 1 minus t. So that's like the height at each point, and I'll be sending x1 sine pi 1 minus t, x2 sine pi 1 minus t, and it will go like xn sine pi 1 minus t. Okay, so now what you need to check is this map is well defined. Well defined in the sense that the square of this, that is cosine square pi into 1 minus t plus x1 square sine square pi into 1 minus t plus xn square sine square pi into 1 minus t, this sums to 1. That is the first thing that we need to make sure, that why this sum is 1. Okay, but you note that here, if I'll take, if my x1 x2 xn on the boundary, so if my x1 dot xn is in Sn minus 1, then what I'll be getting, then you see this is what? This is equals to cosine square pi into 1 minus t plus, so this sine square I'll take common, so and x1 square plus x2 square plus dot dot xn square is 1, so this will be sine square pi into 1 minus t, and this is equals to 1. Okay, that's precisely what we are getting. And you see that if I'll take t to be like 0, so that's like the, so let's write the map clearly here. So gx1 dot dot dxn maps to cosine pi into 1 minus t, and the rest of the thing, so I can write this as in the t times x, and here it's like x times sine pi into 1 minus t. Okay, so this means x1 times sine pi minus 1t, x2 times x3 times xn times. Okay, okay. So what we saw that if x, so let's write this in a vector notation x. So this x means x1 dot dot xn. So if x is in Sn minus 1, then f of x is equals to the North Pole. Okay. Now similarly, what if x equals to 0? Okay. So if x equals to 0, I'll be getting, so that means that t is same as that, like, or I can take t to be 0 because I'm varying the t. So x is not 0, sorry. If t is 0. So if t is 0, okay. So if t, and here is t is 1, and if t is 0, what I'll be getting, I'm getting the center of the this. Okay. And what is that? That will go to, so this all will be like cosine pi will be 0. So this all coordinates will be 0. So I'll be getting cosine pi, and the rest of the things will be 0. So this is equals to minus 1, 0, 0, 0, which is precisely the South Pole. Okay. So you see that now the two extremes are like the thing that we want. Let's see what if t equals to half. So if t equals to half we'll be expecting this circle. Okay. And which is Sn minus 1. So let's see why. So if t equals to half, I'll be getting cosine pi by 2, and now x sine pi by 2. And what is this? This is 0x. And what is this? This is precisely your this one. Okay. So this proves that this is a well-defined map, and it preserves the quotient, it preserves the equivalence relation, that all the points on the boundary goes to one point. Okay, and now this is compact, and this map is a surjective map, so I'll be getting from disk to, sorry, this equivalence quotient space to Sn, I'll be getting a continuous bijective map, and this is compact, this is Hausdorff, so that will give me a homeomorphism. Okay. So in the discussion session, you should try to prove that this map F is well defined. Well defined in the sense that means f of x lies on Sn. Okay, so that is the thing I'm leaving for you to check. Okay, right. So yeah. So now let's come to a bit of projective spaces. So, and again we'll come to this type of thing, that what if we will identify the whole thing to one point. So this type of things we will again be seeing after the projective space. So we saw last time the real projective space, that is RPN, and how do I define that? So we have considered So there are two ways to define it. So one we have already considered, that we consider Rn plus 1 minus 0. That's my x. Okay. And what is the relation I am giving? So I am saying that x is related to y if and only if there exists alpha, of course non-zero, a real number. And let's write minus 0, although we don't have to write minus 0, because such that if an there is this that x equals to alpha y. See, alpha cannot be 0 because x and y are non-zero anyway. So alpha cannot be 0 anyway. So if this is the thing, then we say that x mod this is same as RPN. Okay, so basically then this we say as RPN. That is what we saw in the last lecture, and I ask you to prove that this relation is an equivalence relation. So this is one definition of the real projective plane. Okay, so this is called n real projective plane. Okay, so n stand for that we are doing in Rn plus 1, so that we are getting RPN. So see what exactly we are doing. If you'll see that, so we are like, let's see in R2 what we are doing. In R2, we are considering all straight line which passes through origin but misses the origin. So it's like x equals to my or y equals to mx, whatever. Let's write y equals to mx, where m is non-zero. Okay, so these are all like this. All are like this. It's like this. Okay, and this whole line, okay, we are identifying to one point. Okay, so this whole line, so if I'll write this as Lm, so m stands for this real number, so I can write this as Lm. So each equivalence class will have this. So Lm so that m is non-zero. So each Lm I am identifying with one point. Okay, so that is what precisely we are doing. That any point on this are identified to one point. Okay, this is the geometric picture of this. So it means that in real projective plane, we are just identifying the whole line to one point. Okay. And the same thing we will be doing in the complex projective plane. We'll be considering Cn plus 1 minus 0 and consider a line and identify to one point. But we'll see it in a different way. Now, a second way to define this projective plane is via the sphere. So considering Sn, okay, so I'll consider Sn, and I'll just take antipodal points. So that means x and minus x are related. So I'll just take the x is related to y if and only if y equals to minus x. Okay, so or plus minus x, sorry, both things. So it means that it is like the point is also related to that as well as to the other points. Okay, so x is related to y if and only if this happens. So we are identifying the antipodal points. Okay, and x mod this is same as RPN. So this is also one model for the real projective plane. So maybe I'll ask the mentors to discuss this thing, like at least a sketch of this thing, that Sn mod this it's same as RPN. So we saw two definitions, this as well as Rn plus 1 minus 0 mod this is RPN. So try to see that why these two definitions are same. So it means that if I consider this as my definition, I should be able to prove that this quotient space is my RPN. Although this requires some extra thing, so probably we have to like see whether we can discuss this or not. But I'll ask some mentors to discuss it if possible. Okay. So, but these are the two, at least two notions to define the real projective plane. There are other notions, but at least these two notions we should know. Okay. See, last time we also saw that like if if some group is there, if some space is there, and if some group acts on this, then X mod G is some quotient space. And here it's see what is happening. You have X is Sn, and if I take my group as Z2, because this is the Z2 is acting here, and this is precisely the space that Sn mod Z2. So if I that on Sn the group Z2 that Z mod 2Z is acting, and that will be giving me the sphere. Sorry, real projective plane. So there are lots of ways to define, and all are identical. Okay. So this is the real projective plane, and similarly, I can define the complex projective plane, but I'll not go to that. Let's stick to the real projective plane only. Okay. So now just to give you some topological properties. So since Sn is compact, this RPN is compact. It's connected. This is connected. Okay, and now you also need to try to prove that RPN is Hausdorff. Okay, yeah. So this you should discuss among yourself in the discussion session. Okay, so yeah, right. So let's come to again this sphere to disk to sphere example. Okay, so see what is exactly happening in the disk to sphere example. It's like the whole this goes to one point, this goes to on the circle, this goes to somewhere else. It's like that, okay. So, and in the last lecture, we saw that something called, like if I define on R2 a relation like xy is related to x prime y prime, if and only x square plus y is same as x prime square plus y. Okay, this type of relation we have seen in the last time. And what exactly is this? So this is like all the level curves we are identifying to one point. Okay, so f of xy equals to c is identifying to one point. Okay, and this basically is a very like a generalized theorem that when I leave it to you to discuss, because this is the proof is exactly same as what we have discussed the previous theorems, like if x is x to y, we have a space which preserves the equivalence relation, then we will get a continuous map from the quotient space. So the theorem states that if f to x, if f from x to y be a open or a closed map. So what do I mean by open map? So open map means if u is a subset of x that's open, then f of u inside y is open. So if this is open, then this is open. Same as closed. Okay. So now you see that we saw that basically if x is compact, y is Hausdorff, f is continuous, bijection, then f is an open map. That is precisely what we have proved. So this theorem says that this we are assuming that, so we are not assuming X is compact or all. So if X to Y, if this is open or closed map and this is continuous and surjective map, so this is continuous, surjective. Okay, if all this happens and Y, and now what is the thing? Then Y is homeomorphic to the quotient space. Okay, and what is the relation? The relation is that X, this relation is, let me write this, is, so all the label sets of F to one point. So I'm writing, so this is like all the label sets of F is identifying to one point. Okay. Okay. So it means that if f of xy equals to c for some constant c, then this xy are identifying, or not xy, it's like now it's only x because that's arbitrary space x. So if f of x equals to c, so this set of all x's, then f of x equals to c, this all things identifying to one point. Okay, so this is basically the thing. Okay, so this is again a very important theorem to characterize many of the quotient space. Many of the quotient space you can characterize with this. So yeah, so this you can try to prove it, and if you find any difficulty, you can just put those in the Discord server so that the mentors can see and we can discuss the proof of this. Okay, so right. So now let's come. Yeah, now we'll be coming to some. So I'll be discussing two things. Um, right. So I'll be discussing something called cone and suspension, and then I'll stop, I guess. Yeah. So cone. Okay. So now the thing is that, as I told, if you have a space X, okay, and I'll just consider like some subset Y and identifying this Y to one point. Okay. So this type of thing now we'll be discussing. Okay, so let's see that. So that is something called cone. So you see that usual cone that we have studied even in high school is like we have this thing. So what is this? So if you take a cylinder and if you like the whole this the lower circle, if you collapse to one point or if you identifying to one point, I'll precisely be getting this. Okay. So this is basically we want to generalize to any arbitrary space. So how do I do that? So you see that how can I write the cylinder? So cylinder I can write S1, the circle, I'll take a circle and I'll just take the product with 0, 1. So this is my S1 cross 0. This is my S1 cross half. This is my S1 cross 1. And what we are doing, we are taking all these points on the like all this S1 cross 0, I'm identifying to one point. Okay. Okay, so that sometimes we write like okay, we'll just consider S1 cross 0, 1, that's the space, and we are identifying this to one point. So this is the meaning of that. For example, in the disk example, we are doing disk with Sn minus 1. Okay, so this means that all points which are on this subset which identifying to one point. Okay, and remaining is doing nothing, like all the points are related to itself. Okay, So it means that if I'll write down the equivalence class of this, so if x times t, so x on the circle and t is this, so what is this? This is equals to xt. Okay, if t is my not 0, and if t is 0, this is a point. So this is my x is varying on this on the circle. Okay, and otherwise this is otherwise what? Otherwise it's 1 point. Okay. So, and that precisely we called as a cone. So this is the definition. So if I have any space, any topological space X, if I take any topological space X, so consider X cross 0, 1. So this is my X, and I'm considering my X cross 0, 1. Okay, so this is my X cross 0, 1. And I'm now the cone, which will be writing C of X. So C of X, so this is my cone of x, and this is defined as x cross 0. Or you can define as x cross 1 also. This is just like, so this is also same as x cross 1. Okay, that's same. Okay, and this is we call as a cone of x. Okay, so yeah, so let's see some of the examples. So what if I'll take x as a point? Okay, so if x is a point, what is the cone of x? So see, if x is a point, what is x cross 0, 1? That's just this, the line this. Okay, this is my x cross 0, 1. And now the lower part is just a point. So identifying this point remains same. So this cone is what? So the cone of x is line segment, or is same as 0, 1. Okay, let's take x to be 2 point. So again, what will be the cone? So I'll take the product. The product will be 2 copies of line. And now we have to identify these 2 points. So what I'll be getting is like this. This is my cone of x. Okay. Okay. Similarly, if I take 3 points, the cone will be what? The cone will be the this kind of thing. Okay. This is called this is the basically cone of 3 points. So cone of n points will be like you'll just take n many lines will be 1 point. Okay, so this is the cone of n points. Now what about the cone of let's take cone of circle S1. So we saw that this is the thing and this. Okay, then what is this? If I'll do, this is precisely my this thing. Okay, so this is my cone of S1. Okay, and what exactly is this? We want to identify it. What exactly is this? Is this some known space that we want to know? Is this some known space? So I recommend you to pause the video here and try to think if the cone of circle is some known space that you know. Okay. So because okay, so let's discuss what is this. So you see that so you see here we have a kind of disk. Okay, like the circles is the radius is getting smaller and smaller and smaller and going to this. So what we believe that this is same as the disk. Okay, so the cone of circle is homeomorphic to the disk. Okay, and the proof is again very easy. So I So how will I go for a proof? So I'll do S1 cross 0, 1. I'll define a map from this to a disk so that it preserves my equivalence relation. All the time the same thing. Okay. And now you're using this is what you call the compact first drop thing. Okay. And how will I define the map? Do you have any idea? See what is exactly happening. So this circle is going to point. This circle remains this. This circle, the radius is getting stretched. Sorry, the compressed. So if I'll take any point x on the circle and t, I'll be just sending to tx. Okay. Okay. So if I'll take any point x, I'll be sending to tx. And now what happened? You see that if t equals to 0, this point is 0. So this all point become 1 point. Okay. So, and so this will give me a well-defined map between these two, and that will induce a homeomorphism also. And this is beside, and this is this is what? This is your continuous surjective map. It's a surjective map. This is compact. This is house drop. So this will be compact. This is house drop. This is a bijection. So compact bijection will give you a homeomorphism. Continuous compact bijection. A continuous bijection on a compact to house drop space will give you a homeomorphism. So this will prove that the cone of circle is nothing but the disk. Okay. So a problem or an exercise for the discussion session that you can try is the cone of Sn is or Sn minus 1 is D. Okay, so you try to prove that. Okay, now let's come to something called suspension. So what is this? So see, what we did in the last example, we take a cylinder and identify this to 1 point. So this we are identifying 1 point. We'll be getting like that. But now we want that what we'll do, we'll identify this also to 1 point. Okay, so I'll be getting like, I'll be identifying this also to 1 point. So it's like, I'll be getting like this. Okay, so it's like double cone kind of thing. Okay, so that is we called as a suspension of x, which we usually denote by if x is a space. So suspension of x is like this, or we can denote by s of x, whatever you do it. Okay. So how will I define? So I'll take x cross, let's take minus 1 to 1, and identifying with what are the things that we are identifying? We are identifying two things. One is like x cross 1 and followed by, so if I'll write this as x cross 1, and in this space we are identifying x cross minus 1. Okay, so this is one way, but that is same as, okay, this is the thing, but this is same as, if I write this, that's same as x cross minus 1 to 1, and I'll take x cross 1 union x cross minus 1. Okay, so it means that I'm taking x cross minus 1 to 1 and identifying the lower part and the upper part. So that we call as a suspension of x. So see, these spaces will be useful when we later read the topology, like something called algebraic topology. So this is very much useful in algebraic topology. So that is beyond the scope of this course. But this type of spaces, cone, suspension, are very much useful in in those kind of study. So let's see a bit of example. So again, starting with point. So what is the suspension of x if x is a point? Again, it's what? I'll take x cross minus 1 to 1, but this is nothing. Again, like identifying this to 1 point, this to 1 point won't change anything. But if I'll take 2 points, Okay, I'll be getting like this. And if I'll identify these two, so I'll be getting like a rhombus kind of thing. Okay, and what is this? This is circle, huh? Because homeomorphic to circle, because this is like kind of this arc and this is kind of this arc. So this is circle. Okay, so try to prove this. Okay, so in the discussion session, you should try to prove that the suspension of 2 points, let's write x1 and x2, is homeomorphic to circle. If I'll take any 2 point, the suspension is circle. Okay? Okay. And you should also prove that suspension of Sn, if you take, that's like Sn plus 1. Okay. So these all I leave it to for the discussion sessions. So all are like for discussion sessions. At least you should be able to prove this by your own. Okay. That's not difficult. Okay. So yeah, so there are lots of things to discuss, and I'll stop here because these are completely new to many of you, and it will take time to digest this type of things. So I encourage you all to go back and discuss as much as possible among yourself. If you find any difficulty, you can ask to mentors or me also. Okay, and you can, like I was following most of the times, there is a notes by Kumar, and that's called Quotient Topology. So it's on the web. So this is what I was following most of the time. It's by Kumar expository note. So if you'll just Google it, Quotient Topology Kumar, you will be getting a note, and I was mostly following this article. Okay. Okay. So I hope you have learned something out of this Svādhyāya 1.1, 1.2 with these three lectures, and I wish you all a best of luck in your future journey. Okay.